Copilot is everywhere in Microsoft 365. It sits in Word, Excel, Teams, and Outlook, and it's likely running in a dozen other places your organization uses every single day. But here's the problem. Most of the time, your teams are using it wrong. They are specifically using it wrong when they ask it to predict the future. The assumption people make is that Copilot is a reasoning engine that can read data and figure out what comes next. You type a prompt like, "What will our Q2 sales be?" and you expect Copilot to digest your historical numbers, understand your business context, and return a forecast. It feels simple and intuitive, but it is completely wrong. In reality, Copilot is a reasoning engine that works over language patterns rather than structure. It sees your tables, but it doesn't understand the relationships between them. It reads your numbers, but it has no idea what those digits actually mean for your specific business. The result is a tool that is confident, eloquent, and frequently hallucinating. This episode is about closing that gap. We aren't trying to make Copilot smarter. Instead, we are building architecture around it so that Copilot becomes what it's actually good at. We want it to orchestrate structured logic instead of just pretending to be a logic engine itself. We are moving away from the idea of chatting with spreadsheets and moving toward building systems where Copilot interprets what a person is asking for. Then, it delegates that request to a real predictive engine grounded in your semantic layer. We will expose exactly what is broken, show you how to fix it, and walk through the architecture that makes it work. There is no marketing language here, just structural clarity. The Copilot prediction problem. Every week, organizations ask Copilot the same kinds of questions. They want to know what customer churn will look like next quarter, or they ask for a revenue forecast for the next fiscal year. They might even try to find out which products are most likely to see demand spikes. These are legitimate business questions, but the problem is what happens the moment you hit enter. Copilot generates an answer that sounds plausible. The numbers look reasonable, the confidence level seems high, and you decide to act on that information. Then reality hits, and the actual results don't match what Copilot said at all. This isn't some random fluke. It is exactly what happens when you ask a language model to predict the future without giving it the structure it needs to function. The reason is simple. Copilot doesn't understand what revenue means in the context of your specific business. It doesn't know if that number includes refunds or excludes them, and it has no idea if you count revenue by the invoice date or the delivery date. Because it hasn't ingested your actual data, it doesn't know your seasonality patterns. It is working from pattern recognition at the token level rather than using actual business logic. And here is the thing, it can't do math. It cannot do the kind of real math that matters for a serious prediction. What it actually does is approximate language patterns. If the training data showed thousands of examples where Q1 sales followed certain patterns, Copilot can guess at something that sounds plausible. But it is still just a guess. It is a sophisticated, eloquent guess, but it is a guess nonetheless. The confidence is the real killer here. Copilot never whispers its uncertainty. It states its predictions like they are absolute facts. A user reads a sentence like, "Based on historical trends, your Q2 sales will likely reach $3.2 million, and they assume they are looking at real analysis. They think Copilot has actually done the math when it hasn't done anything of the sort. There is another layer to this problem. Copilot doesn't know the difference between a forecast and an actual. It doesn't know which tables in your data warehouse contain real numbers and which ones are just projections. It doesn't understand your business rules, and it cannot execute filters based on your company's specific logic. It just sees data and tries to match a pattern. When the data is messy, which is the case in almost every real organization, Copilot doesn't flag the mess, it just absorbs the mess and passes it along. If your historical sales data has inconsistent definitions across different regions, Copilot won't catch that error. It just predicts using all of it equally, which only serves to amplify the noise. Most organizations think this is a Copilot problem, but it's actually an architecture problem. Copilot is doing exactly what it was built to do by reasoning over language and generating plausible outputs. But you are asking it to do something that requires structured computation, business logic, and data governance. You're asking it to be a data analysis engine when it is actually a language model. The gap isn't Copilot's fault, it's ours. Why natural language queries fail at prediction? Let's get specific about what happens when you type a question into Copilot. Imagine a user opens Power BI to look at a dashboard full of sales data. They click the Copilot button and type a simple question. What will our Q2 sales be? The question is clear, it's reasonable, and it is exactly the kind of thing any human analyst should be able to answer. But from Copilot's perspective, it sees something very different from what the user thinks it sees. Copilot sees a collection of tables, columns with numbers, and maybe some dates or product categories. But here's what it doesn't see. It doesn't see relationships. It doesn't understand that the sales amount column in Table A needs to be joined with product ID in Table B through a specific business rule. It sees tables instead of a graph, and it sees numbers instead of measures. More critically, Copilot doesn't see business logic. It doesn't know that revenue in your organization means invoiced sales excluding returns and credits, calculated on the invoice date rather than the delivery date. It doesn't know that your fiscal year runs on a calendar different from the calendar year, and it has no idea which regions use which currencies or whether certain product lines are being phased out. Those things live in your semantic model, but they are not in the raw tables Copilot can access. When Copilot reasons about this data, It is doing something very specific. It is predicting the next token in a sequence based on patterns in its training data. That is literally what language models do. They see a pattern and they predict what comes next. If you feed in Q1 sales were $2 million, Q2 sales were $2.3 million, Q3 sales were. Copilot will generate a plausible next number. It is sophisticated statistical pattern matching, but it isn't prediction. It is just extrapolation with a lot of confidence. The problem is that real prediction requires something else entirely. Real prediction requires understanding causation rather than just correlation. It requires knowing that a sale happens because a customer decided to buy, not just because the calendar page turned over. It requires understanding seasonality as a structural fact about your business rather than a pattern in historical data. If demand drops 20% every summer because your core market goes on vacation, that is knowledge, and Copilot simply doesn't have it. And this is where it gets worse. Copilot has no mechanism to know what it doesn't know. It doesn't have a way to signal uncertainty or say that it's working with incomplete information about your business model. It just generates an answer and assigns a confidence level, and the user interprets that confidence as justified because Copilot sounds so authoritative. This is the fundamental mismatch. Language models work by finding patterns in sequences, but prediction requires structure like causal models, business rules, and validated assumptions. One is about language, while the other is about logic. You could try to fix this with better prompts by telling Copilot to consider seasonality, regional variations, and product mix changes. Copilot will incorporate those words into its output, and it will sound much smarter, but it will still be guessing. Because Copilot cannot execute logic, it can only reflect language patterns back at you. The solution isn't better prompts or training Copilot harder. It's architecture. You need to give Copilot a structured layer to reason over, which means using a semantic model that encodes your business meaning instead of raw tables. You need to build actual predictive models in code that are grounded in real data science. Then, Copilot's job becomes orchestration, where it interprets what the user is asking for and routes that request to the right structured system to actually answer it. That shift from Copilot as a calculator to Copilot as an orchestrator is what this entire episode is about. What Power BI semantic models actually are. A semantic model is not a database view. If that is what you think it is, you need to stop now and recalibrate. A view is just a filtered slice of raw data organized by SQL, but a semantic model is something fundamentally different because it is a layer of meaning. Think of it this way. A semantic model is a machine-readable contract. It is an agreement about what your data represents and how it should be used. It sits between the raw data and the tools that consume it, like reports, dashboards, and now Copilot. Everything that lives in that contract is explicitly defined rather than inferred. Start with the tables. In a semantic model, tables don't just exist, they are documented. A table called sales has a description that says exactly what it contains, like completed transactions with revenue recognized on the invoice date. That description isn't just narrative flavor for the humans, it is operational because Copilot reads it, your analysts read it, and the tools read it. The same rule applies to columns. A column called amount comes with a decimal type rather than a string, and it is formatted specifically as USD currency. It includes a description that defines what that amount represents in business terms, such as whether it is gross or net, or if it includes shipping costs. All of that is explicit. Then come the relationships. This is where semantic models diverge sharply from raw databases. In your data warehouse, you might have a junction table that links customers to orders through a foreign key, but in your semantic model, that relationship is labeled. It has a direction, it has a cardinality, and it has business context. The semantic model says this is a one-to-many relationship from customer to order, and because it is active, Copilot knows this is the path to use when correlating customer attributes with order facts. The raw database just has keys, but the semantic model has meaning. Hierarchies live here too. Your date dimension probably has relationships where years contain quarters, quarters contain months, and months contain dates. In a database, that is just normalization, but in a semantic model, you explicitly declare it as a hierarchy so that Copilot and your analysts can navigate time intelligently. Asking to see sales by month while drilling into weeks for this quarter makes sense because that hierarchy is encoded. Now we get to the core, the measures. Measures are where business logic crystallizes into an executable form. A measure is a calculation expressed in DAX that defines a metric. Total sales isn't just a sum of the amount column. It is a sum of the amount for all rows where the order status is marked as completed and no return has been processed. That logic is baked in. When Copilot asks for sales, it doesn't have to guess because the semantic model has already defined what that word means. This is the revelation that changes everything. In a raw table, the word sales is ambiguous. Are you summing all amounts or are you filtering for specific statuses? Are you including returns or excluding them? Copilot has to guess. In a semantic model, sales is the measure, which makes it unambiguous, so Copilot can reason over it with confidence. Row-level security and object-level security sit here as well. Row-level security means a specific user can only see sales for their own region or product line. Object-level security means a user can't even see that a column exists if they don't have authorization. These are not report-level settings. They are semantic model-level rules that apply everywhere the data is consumed, whether that is in a report or a Copilot query. This structure of tables with definitions, relationships with direction, and measures with calculation is a contract. It is an agreement that this is what the data actually means. And because it is machine readable, Copilot can parse it and use it to generate trustworthy outputs instead of hallucinations. That is why semantic models matter for prediction. They are not just a way to organize things, they are meaning made explicit. The role of metadata in Copilot reliability. You can build the most sophisticated semantic model in the world, but Copilot will still fail if the metadata inside it is sparse or vague. This is the underrated lever in the entire system. Here's the specific mechanism. When you ask Copilot a question, it doesn't directly query your semantic model. It first tries to understand what you're asking for, which means it has to identify the right table, the right measure, and the right filters. It does this by reading the descriptions you've written, the column names, the measure definitions, and the synonyms. All of that textual context is how Copilot figures out what you actually mean. If those descriptions are weak, Copilot guesses, and it guesses with total confidence. Imagine you have a measure called revenue with no description at all. Copilot sees the name, but it doesn't know if you mean total revenue, net revenue, or revenue by customer. It doesn't know if returns are included or what the time period is, so it makes an assumption. Sometimes it's right, but often it's not. The user never finds out until they check the underlying numbers and realize Copilot was working with a different definition than they thought. Contrast that with a measure that has a real detailed description. If the metadata says total invoiced sales in USD, excluding returns and credits processed within 30 days of invoice date, Copilot finally has context. When a user asks what last month's revenue was, Copilot understands exactly which measure to use and how to filter it. The same logic applies to your column descriptions. A column called status could mean order status, payment status, or even customer status. Without a description, Copilot has to infer the meaning. A description that explains that order status is the fulfillment state of the order at the time of query removes all ambiguity. Synonyms matter enormously here. Your semantic model might define a measure called total revenue USD, but your business team calls it sales or the top line depending on the context. If you don't register those synonyms in the metadata, Copilot won't map the user's language to the right measure. They'll ask what the sales were last quarter, and Copilot will either say it can't find that measure or it will return something completely unrelated. Business glossaries and term definitions layer on top of this. A term like customer churn means something very specific in your organization. Your definition might state that a customer is considered churned if they have made no purchases in the past 90 days after having made at least one purchase in the prior 180 days. That definition is operational. Copilot uses it to understand not just what you're asking for, but exactly how to calculate it. Without this metadata richness, you're asking Copilot to operate in total ambiguity. With it, you're giving Copilot a shared language with your organization. Microsoft has recognized this and made it systematic. The Prepare Your Data for AI feature in Power BI is now a first-class workflow. It's not buried in documentation tabs, but is instead a guided process. You go through your semantic model and you write descriptions, you define synonyms, and you tag which fields are safe for AI to use. All of that becomes part of the model itself. This is the shift that matters most. Metadata used to be documentation that lived in a wiki somewhere separate from the data. Now metadata is operational infrastructure. It's how Copilot understands your business, and it's how your predictive models stay aligned with your reports. When you're evaluating your semantic models for Copilot readiness, don't look first at the data volume or the table count. Look at the descriptions and the measure definitions. Count how many columns have no description at all. That gap between data and metadata is exactly where Copilot fails. Introducing Semantic Link as the bridge. So far, we've established the problem. Copilot can't predict because it has no structured foundation to reason over. We've built the semantic model as that foundation, which is a layer of meaning that encodes business logic and security rules. Now comes the critical question. How does Copilot actually access that semantic model? And more importantly, how does a real predictive engine access the same business logic so that predictions stay aligned with reports? The answer is Semantic Link. Semantic Link is a feature in Microsoft Fabric that does one fundamental thing. It exposes your semantic models to code. Not to reports or dashboards, but to Python and PySpark. It's for any data science workload that needs to reason over your business logic without rewriting it from scratch. This is not a new database or a new reporting tool. It's a programmatic interface. It's a bridge that allows code to query your semantic model the same way a report does. It uses the same measures, the same security rules, and the same table relationships. Think about what this means structurally. Right now, in most organizations, the BI team builds a semantic model in Power BI. They define measures and set up security. That model powers reports and it's locked down and audited. Meanwhile, your data science team is off in their own world using Python notebooks. They're working with raw data or SQL queries, and they're rebuilding metrics from scratch because they don't have access to the BI team's definitions. They define revenue one way, and the BI team defines it another. Nobody knows which is right until someone compares the outputs and finds a discrepancy. Then you spend weeks reconciling definitions. Semantic Link eliminates that split. It says the semantic model is the source of truth. All predictive code should run through it, and all metrics should use the same definitions. The implementation is a Python library called SemPy. You import it in a notebook and point it at your Fabric workspace. Suddenly, your code can access your semantic model programmatically. You can list tables, you can list measures, and you can see the DAX definitions behind those measures. You can execute DAX directly from Python and get results back as a data frame. You can read semantic model data into Spark for distributed processing while maintaining the full context of relationships. This changes everything about how you build predictive models. Before Semantic Link, a data scientist would write a query to pull historical revenue data. They'd calculate a trend and build a model. It would use a different definition of revenue than the reports, so everyone would argue about which number is right. With Semantic Link, a data scientist imports SemPy. They call a function to list all measures in the semantic model. They find the total revenue measure, check its description, and see exactly how it's calculated. They use that same measure definition to pull training data for their model. Their model inherits the semantic model's logic. When they deploy the model and expose its outputs as a new measure, that measure uses the same definitions as everything else in the organization. There is no discrepancy and no argument, it's just one source of truth. This is also where Copilot integration becomes possible at scale. Copilot doesn't need to understand how to predict, it needs to understand how to ask for predictions. It needs to know those predictions are grounded in the same semantic logic that powers your reports. When Copilot routes a user's question to a predictive model, that model can read the semantic model through SemPy to understand exactly what data to use and what security rules must be enforced. The bridge isn't magic, it's access. Semantic Link is access to business logic, access to definitions, and access to security. It's the foundation that makes predictions trustworthy instead of just plausible. How SemPy exposes semantic models to code. Let's get concrete about how this actually works. When you open a Fabric notebook and start working, SemPy changes the entire nature of your workflow. You start by importing the library and authenticating to your workspace, and immediately you have full programmatic access to every semantic model in that environment. You can call a simple function like Fabric. List datasets to see every model available to you. From there, you can drill deeper by calling list tables to see every table, its description, and the specific data types within it. If you call list measures, you'll see every single measure, the DAX formula behind it, and exactly which column it belongs to. This isn't just looking at data, it's introspection at the semantic level. But here's where it really matters for your daily work. Imagine you're building a predictive model and you need historical sales data to train it. Before SemPy, you'd have to write a complex SQL query and handcraft a join between your fact and dimension tables while hoping you got the relationships right. With SemPy, you don't write the join because the semantic model has already defined it for you. You simply call a function that reads the data directly into a Spark data frame, and the relationships, column names, and filters come with it. You aren't reconstructing business logic from scratch, you're inheriting it. And there's more to it than just reading tables. You can now execute DAX directly from your Python notebook. This is a massive shift because DAX is where your business logic lives, including your time intelligence and measure definitions. Normally that logic only runs inside Power BI, but SemPy lets you evaluate those expressions from your notebook. You can write a DAX expression that sums revenue for the last 12 months while automatically handling your fiscal calendar and specific filtering rules. You execute it from Python and get the results back as a data frame. Your predictive model is now using the exact same calculation that your executive reports use. Think about the errors this prevents in a typical organization. In the old model, a data scientist would try to replicate that last 12 months logic using pandas code and date filters. They'd probably get it slightly wrong because the company's fiscal year doesn't align with the calendar year and nobody thought to tell them. Their training data would be off, their model would be calibrated to the wrong numbers, and your reports would eventually show one number while the model suggested something else. That leads to confusion, misalignment, and endless arguments about which number is actually right. With SemPy, that conflict disappears because there's only one calculation and one answer. The DAX runs the same way whether it's powering a dashboard or feeding a machine learning model. You can also evaluate measures with very specific filters and groupings. You might ask for total revenue for each product category, filtered to the West region for the last quarter, and SemPy will construct that query and return a data frame. The semantic model applies your row-level security automatically, so if a user only has access to certain regions, those rules are enforced here too. The aggregations follow the official measure definition, not a guess at what the definition should be. This creates a unified foundation for your entire data strategy. Your predictive models aren't just compatible with your semantic model, they are built directly on top of it. They use the same measures, they respect the same security rules, and they inherit every definition you've already built. When you deploy a model and expose its output as a new measure, that new data is automatically aligned with everything else in the system. This enables a fundamental structural shift in how teams operate. Your data science team stops asking for manual data exports, they stop writing custom SQL, and they stop maintaining their own parallel definitions of revenue. They work through the semantic model, which means everything they build is rooted in the same logic that powers the rest of the business. Discrepancies vanish because there is only one source of truth for every metric. Your data science and BI teams are no longer working in separate universes. They are finally working in the same one. That alignment is the only way to get predictions people actually trust. The architecture, where prediction actually happens. To set this up correctly, you have to understand what's actually happening under the hood. This is fundamentally different from how most people think Copilot works. The reality is that Copilot does not predict. I'll say that again because it contradicts almost all the marketing you've seen. Copilot does not forecast, it does not calculate, and it does not run statistical models. What Copilot actually does is orchestrate. The actual prediction happens somewhere else entirely. It happens in a Python notebook, a Spark job, or an R script running inside Fabric. That code uses Semantic Link to pull data and measures from your semantic model, and then it runs a real statistical model like ARIMA or gradient boosting. That code produces the actual number, the forecast, or the churn score. Copilot's job is to handle the interface. It takes the user's natural language request, like, what will our customer churn be next month, and passes the intent. It understands what churn means and identifies the time horizon the user is asking about. Then Copilot makes a decision about which model should answer the question. It checks if a churn model exists and verifies if the user has permission to see it. If everything checks out, Copilot routes the question to that specific model. Once the model runs and returns a result, Copilot does what it's actually good at. It contextualizes the data. If the model says churn will be 8.3%, Copilot explains that based on 12 months of history, we expect that specific percentage of customers to leave. It can even explain that the prediction is accurate within a certain range and point out that a seasonal uptick is the primary driver. The explanation comes from the language model, but the number comes from the predictive model. The data comes from the semantic layer. Each part of the system is doing exactly what it was built for. This is the big architectural shift you need to understand. Copilot isn't the calculator, it's the translator. It turns user intent into a structured query for a predictive system, and then it turns that system's numerical output back into a human-readable explanation. This matters because it allows the system to be honest about uncertainty. If the predictive model says the confidence interval is 1.2%, Copilot communicates that clearly. If the model was only trained on 6 months of data for a specific segment, Copilot can flag that the forecast should be taken with caution. It can even mention known biases, like a tendency to underestimate outliers. The system becomes transparent about what it knows and what it doesn't. Compare that to the current state of AI, where a basic Copilot tries to predict things directly. It has no sense of uncertainty or caveats. It just generates a number that sounds plausible and moves on, even if that number is a total hallucination. This architecture also means your capabilities scale without needing Copilot to get smarter. As you improve your predictive models by adding more data or refining your statistics, Copilot automatically gets better because it's routing to superior models. Copilot itself hasn't changed, but it now has better systems to coordinate. Governance also becomes universal across the platform. Because your predictive model runs through Semantic Link, it inherits the row-level security of the semantic model. A manager in the West region will only see predictions for the West, and a user without access to a specific product line won't see churn data for it. You don't have to tell Copilot any of these rules because the semantic layer handles them automatically. This is the only architecture that makes AI-driven prediction trustworthy. It isn't about Copilot doing the work. It's about Copilot coordinating the work while specialized systems and a strong semantic layer ensure everything stays accurate and secure. Building predictive models on the semantic layer. Let's look at how this actually works when you're on the ground. You have your semantic model ready, your measures are defined, you understand the architecture, but now you face the real challenge. How do you build a predictive model that lives inside this structure instead of sitting off to the side? It starts with your measures. You aren't looking at raw tables here. You're looking at the calculated fields that already hold your business logic. Total revenue, active customers, customer lifetime value. These metrics represent how your organization actually functions, and because they live in the semantic model, they are already consistent and documented. This is the foundation of your predictive work. When you open a Fabric notebook, you import SemPy and authenticate your workspace. From there, you pull the specific measures you need for your training data. You aren't stuck writing complex SQL or manually joining tables while praying the cardinality is right. Instead, you call SemPy functions that evaluate those measures across your history. It automatically respects your relationships and hierarchies using the exact same logic that powers your executive reports. What you get back is a clean data frame, structured exactly the way your business defines its success. Once you have that grounded data you start building, maybe you need a time series forecast for revenue using ARIMA, or perhaps a classification model to predict customer churn with gradient boosting. You might even be clustering your customer base to see who is most likely to buy a new product. The specific math doesn't change the fact that your training data came from the semantic layer. Your model is learning from data that was already cleaned and aligned with how the company sees itself. This inheritance is the part you can't skip. When you train on data pulled through SemPy, your model isn't just compatible with your system, it is grounded in it. The version of revenue your model learned from is the exact same version your dashboards show every morning. There is no data drift and no awkward translation layer where definitions start to diverge over time. Security rules follow the data too, even if you don't see them working in the background. When you pull history through SemPy, any row-level security rules in the semantic model apply instantly. If your organization segments data by region and your notebook user only has access to the West, SemPy only returns West region data. Your model trains only on what that specific user is allowed to see. When the model is deployed, users only see predictions for the areas they are authorized to access, all without you writing a single line of security code. After the model is validated, you don't just leave it sitting in a notebook. You deploy it by creating a new table in your Fabric lakehouse or warehouse to hold those predictions. You might call it churn predictions, where rows represent customers and columns show the probability of them leaving next month. You've just turned a predictive insight into a permanent data asset. The final step brings everything full circle. You expose those new predictions back through the semantic layer by adding a measure like predicted churn rate. The DAX behind this measure aggregates your prediction table and calculates the metric for the whole company. Now, Copilot can see that measure just like any other. When a manager asks about predicted churn by region, Copilot routes the request to this measure, the semantic model handles the regional filtering, and the result comes back secured and consistent. This is the complete cycle of a modern data system. You start with established measures, build a predictive system grounded in that logic, and store the results as fresh data. By exposing those results back through the semantic layer, your predictive capability is no longer a separate silo. It uses the same definitions, respects the same security, and follows the same governance as your standard BI. Because of this integration, Copilot can finally route difficult questions to models that actually understand what they are predicting. DAX as a language for prediction logic. Most people treat DAX like a simple reporting tool. They think you write a formula to show a number in Power BI and that's the end of the story. But that's a misunderstanding of what DAX actually is. DAX is a language for encoding business logic, and it isn't tied to a single report or a specific visualization. When you write DAX, you are documenting the actual rules of how your business functions. This is a massive deal for prediction because DAX makes your logic executable, machine-readable, and consistent across every system you own. Take a look at a basic example like revenue. For most companies, revenue isn't just a simple sum of every transaction in the database. It might only include invoiced transactions from completed orders, excluding any returns processed within 30 days, all calculated in USD based on the invoice date. In a traditional SQL environment, you'd write a long where clause with multiple filters for order status and transaction types. That is just procedural syntax. In DAX, you are writing logic. You use the calculate function to specify a measure and then layer on the business context. You are telling the system to calculate a specific value, but only for these rows and only for these specific periods. The syntax looks like this: calculate amount, orders, order status, complete orders, return date, blank. That isn't just code. It is a business rule translated into a language the computer understands. The real power is that this formula doesn't just hide inside a single report. It becomes a permanent part of your semantic model as a documented measure. Every system that needs that data, whether it's a dashboard, a Copilot query, or a predictive model using Semantic Link, accesses the exact same logic. You can see this power most clearly with time intelligence. Your business likely operates on a fiscal year that doesn't align with the standard calendar, perhaps starting in July and ending in June. A standard data warehouse just sees dates, and SQL doesn't inherently understand your specific fiscal calendar. DAX does. You can use a function like SemPeriod last year, and it shifts the context back by one fiscal year automatically. SQL can't do that without a lot of custom manual logic, but DAX handles it natively. When a user asks Copilot how performance compares to last year, Copilot doesn't have to guess what last year means for your specific company. It simply reads the DAX definition of your year-over-year measures. Since the DAX already holds the fiscal year logic in its metadata, Copilot knows exactly which dates to compare. There is no guessing and no room for reinterpretation. The same logic applies to every filter and calculation you create. These aren't just bits of syntax, they are structural facts about your business. You might have rules that exclude certain transaction types from revenue or define an active customer as someone who bought something in the last 12 months. DAX is the only place where these rules live in a way that the whole system can use. This has a huge impact on your architecture. When you pull training data for a predictive model through Semantic Link, you are pulling data that has already been filtered by these DAX rules. Your model isn't training on messy raw transactions, it's training on business-defined aggregates. Revenue means what the DAX says it means, and customer counts follow the company's official definition of active. This creates a level of consistency that was previously impossible. Your predictive model can't accidentally use a different definition of profit than your CFO uses in the quarterly meeting. The definition is locked into the DAX, making it the same everywhere. This is also why your metadata tagging is so important. The descriptions you write for each measure, the assumptions and the filters you've baked in, become the context Copilot uses to answer questions. A measure with a clear description is transparent and useful, while a measure with no description is just a black box. Copilot can work with the first one, but it will be forced to guess on the second. At the end of the day, DAX is where your business rules become executable code. It is the bridge that transforms raw, meaningless data into actual business value. The security perimeter, RLS and Copilot. Most organizations haven't thought through this next problem yet, but it's going to force a total rethink of how security works in your semantic models. Row-level security is no longer just a reporting control, it is now a Copilot control. That distinction changes everything about how you decide who sees what. In the old world, RLS was simple. You defined roles in your model and gave each one a filter rule. Sales managers in the West only saw West region transactions, while accountants in Europe only saw European cost data. These rules lived behind the scenes. When a user opened a report, RLS silently filtered the data to show only their authorized slice. It was clean, invisible, and predictable. But now Copilot can reason over that data, and this is where the shift happens. Copilot doesn't just look at what's on the report page, it can ask questions that drill into every single corner of the data the user is technically allowed to touch. Think about how this plays out in real life. A salesperson in the West has read access to a model, and their RLS rule limits them to West region transactions. They open a report and see their regional pipeline, which is exactly what you expected. But then they open Copilot and ask for a year-over-year comparison of sales by product category for their specific region. Copilot takes that request and runs it through the semantic model while applying the RLS filters. It returns the comparison, and suddenly the salesperson sees insights that were never in a pre-built report because no one thought to combine those specific dimensions before. This isn't a data breach. The data is there, the user is authorized, and RLS is doing its job perfectly. However, the user now has visibility into analytical slices that no one explicitly planned for them to see. They can ask questions you didn't anticipate. They can discover performance trends that used to require a formal request to the analytics team. This is what I mean by amplification. You aren't bypassing security, but you are amplifying a user's ability to reason over the data they already own. That is incredibly powerful, but it's also why your governance has to become much more intentional. The problem is that most RLS was designed with static reports in mind. You built roles around what should be visible on a dashboard, assuming the user wouldn't ask questions outside of those boundaries. That assumption breaks the moment you introduce Copilot. The user will ask questions that no report ever exposed, simply because they can. The real question you have to answer is whether that's okay. If a manager uses Copilot to find product insights that weren't in the official reports, was that your intention? If the answer is yes, then your RLS is fine. If the answer is no, you have a massive gap in your strategy. This is the point where RLS stops being a technical setting and becomes a governance decision. You aren't just asking what data a user should see anymore. You are asking what predictions and analyses that user should be allowed to request. The answers to those two questions might be very different. Imagine a customer service rep who has access to order history to help resolve issues. In a standard report, they see order details for their assigned customers, which is exactly what you intended, but now they can ask Copilot which of their customers are most likely to churn next quarter. Copilot routes that to your churn prediction measure and applies RLS, so they only see their own customers. They get the answer and start reaching out to at-risk accounts proactively. Is that a good thing? In most cases, yes. It's a perfect example of intended amplification where a rep uses predictive insights to do their job better. But you have to decide that on purpose. You have to design your RLS rules with that specific use case in mind to ensure the role configuration actually allows it. The inverse risk is just as real. If you aren't careful about what data a user can touch, Copilot will find ways to reason over sensitive info you never meant to highlight. A user with basic read access to payroll data could ask Copilot for a comparative salary analysis or ask it to flag outliers. If RLS isn't set up to stop that, Copilot will give them the answer. The architecture is forcing governance out of the abstract and into the concrete. RLS is now the control surface where you decide what users can do with AI, not just what they can see on a screen. The choices you make here will directly shape what happens when Copilot starts orchestrating your predictive models. Object-level security and AI-ready models. RLS handles the rows, but there is another layer of security that is now critical because Copilot can see your entire model. This is object-level security, or OLS. While RLS filters rows, OLS operates at the column level to hide entire fields from specific roles. This distinction is a huge deal when you are getting ready for Copilot access. Think about the difference in how these two work. With RLS, an HR person might only see employees in their specific department. The rows are filtered, but they still see every column, including names, salaries, and performance ratings. With OLS, you can go a step further. You can set it up so that the HR person sees everyone in their department, but the salary column is completely gone. It isn't just blurred or masked. It is hidden. For that specific user, the column doesn't even exist. This is essential for sensitive data like health records, credit card numbers, or disciplinary files. These aren't things you just filter. You exclude them from certain roles entirely. An HR coordinator needs names and departments, but they have no reason to see salary data. OLS ensures they can't see it by making the field invisible within the semantic model itself. Here is the part people miss. Hiding a column in the report interface is not the same as OLS. I see organizations hide salary columns from reports all the time and think they are secure, but those columns are still sitting in the underlying data. If a user clicks the Copilot button and asks a question about pay, they might get a full answer. The data is there, and the report just isn't showing it. Since Copilot has access to the whole model by default, nothing stops it from reading those hidden columns unless OLS is turned on. This is where Copilot's reasoning becomes a liability if your OLS isn't right. Copilot doesn't care about the report layer. It looks straight at the semantic model. If sensitive columns aren't protected, Copilot will use them. A user might ask a simple question about what's driving headcount costs, and Copilot will pull salary data to explain the variance. That data was never supposed to be accessible, but it was because you only hid it in the UI. OLS stops this at the source. You configure it at the model level and specify which columns belong to which security group. Salary data gets a specific classification, and employees only see it if they have the right permission. Copilot inherits these rules automatically. When it looks at the model, it respects OLS just like it respects RLS. Sensitive columns stay locked away. The user can't ask Copilot to show them because, from their perspective, those columns aren't there. This is exactly why the prepped for AI designation exists. Microsoft has a formal process for marking a model this way, and it isn't just a marketing label, it is a governance checkpoint. When you mark a model as ready for AI, you are telling the system that a few things are true. You've provided clear names and descriptions, you've built proper relationships and measures, but most importantly, you've confirmed that RLS and OLS are configured correctly. You've thought about who should have access, and you've tested your roles against Copilot. This certification tells your organization that the model is safe. Users can trust Copilot to give them answers without accidentally leaking sensitive details. Your data science team can build predictive models without worrying about security gaps. Your governance team can audit the model and know exactly what access really means. The Prepped for AI label is the new foundation for your access control. It isn't just saying the model works with Copilot, it is a guarantee that the model has been audited, hardened, and approved for AI-driven analysis. The Prepped for AI certification. Let's move from the theory to the actual process. Microsoft has built a specific workflow in Power BI that turns Prepped for AI from a vague goal into a measurable certification. You don't just declare that your model is ready for Copilot and hope for the best. Instead, you work through a structured checklist to confirm every single element before testing it. At the end of that process, you receive a badge. That badge signals something very specific. This model has been audited and is officially safe for AI-driven predictions. The workflow starts with naming and descriptions. We've talked about this a lot, so I'll keep it brief. Every table needs a clear name, every column needs a description that makes sense to a business user, and every measure needs an unambiguous name with its DAX logic documented in plain English. This isn't just a nice-to-have feature. It is the foundation of the entire system because without these labels, Copilot simply cannot understand what it's looking at. Next, you have to look at your relationships and measures. Your semantic model must be structurally sound, which means tables are related correctly and cardinality is explicitly defined. You need to ensure hierarchies are set up and measures are calculated consistently across the board. This is basic data architecture that has been required for good reporting since the beginning, but now it's a mandatory check for AI readiness. Then we get to the security configuration. You have to configure and test your row level and object level security to ensure they work exactly as intended. You define the roles, specify which rows or columns each role can see, and then run tests to prove those rules hold up. This step forces you to be intentional about governance. You aren't just checking a box here, you are documenting exactly who has access to what and why that access exists. Now we hit the part that is brand new and specific to AI. The fourth requirement is defining your AI schema. This is where you explicitly tell Power BI which tables and measures Copilot is allowed to use. You don't want to expose the entire model by default, so you curate the experience. You might have technical tables used for background calculations or development measures that aren't finished yet. You hide those from the AI. Your AI schema defines the specific surface area that Copilot is authorized to reason over. This curation is vital because it stops the AI from hallucinating. If your model has 30 tables and Copilot can see all of them, it might try to join data that shouldn't be joined. It might find a correlation between two things that aren't actually related just because they happen to be in the same model. By restricting the AI to a curated subset, you ensure that Copilot stays within the boundaries of what users should actually be asking about. Finally, you define your AI instructions. These are natural language guidelines that tell Copilot how to handle confusing requests. For example, your company might have 3 different definitions for revenue depending on the department. A user might just ask for revenue without being specific, so your instruction would tell Copilot to assume they mean total net revenue unless they say otherwise. Copilot reads that instruction and follows it every single time. The certification process walks you through every one of these steps. You confirm the names are clear, validate the security, and set the AI boundaries. Once that's done, the model is officially marked as prepped for AI. This badge tells your team that the model has passed a real governance review and is approved for predictive access. It turns the model into something data scientists can build on and something Copilot can reason over reliably. This isn't just more bureaucracy, it's a guarantee of quality. Semantic Link Labs and governance automation. You've prepared your first model, it's certified, and it's ready for the AI. But in a large organization, you don't just have one model to worry about. You likely have dozens or even hundreds of them spread across different teams and business units. Some of these are well maintained, but others have been neglected for years with metadata that hasn't been touched since 2019. If you want to scale Copilot across the whole company, every single one of those models needs to meet the same high standards. This is where manual governance falls apart. You cannot audit hundreds of models by hand, and you certainly can't update every description one by one. You need a way to handle governance at scale, and that is exactly why Semantic Link Labs exists. Semantic Link Labs is a specialized toolkit built on top of the standard Semantic Link. It isn't a new product, but rather an enhancement that gives you programmatic access to tasks that used to require clicking through the Power BI interface. You can manage roles, configure security filters, and update descriptions across hundreds of models using a single script. All of this happens through code in a Fabric notebook, which is much faster than manual work. Take role management as an example. Usually you'd have to open Power BI Desktop, create a role, and set up the filters for every single model. If you have 50 models, you're doing that work 50 times. With Semantic Link Labs, you write one Python script that defines the role and its filters, and then you apply it to all 50 models at once. This ensures that your security is consistent across the entire environment. The same logic applies to managing users. Instead of manually adding people to roles, you can write a script that talks to your HR system. When a new person joins the sales team, the script identifies them and automatically adds them to the correct roles across every sales-related model in the company. When they leave, the script removes them. This turns governance into an automated workflow rather than a chore for your admins. Metadata management scales in the same way. If you need to ensure every measure has a description, you don't have to check them manually. You can run a validation script that scans every model, flags anything that's missing a description, and generates a report. From there, you can batch update those descriptions using templates or have your team review them in bulk before they go live. Translation is another huge pain point that this toolkit solves. If your company operates globally, you need your model descriptions in multiple languages like Spanish, French, and German. Instead of translating these by hand, you can write a script that sends your English descriptions to a translation service and populates the results back into the models. This allows you to update every language version simultaneously without the manual effort. Naming standards are where this gets even more powerful. Your organization probably has rules about how measures and columns should be named. Labs can scan your entire fleet of models and flag any violations, like a measure named revenue that should be measure net revenue USD. The governance team gets a clean report of these issues and can decide which ones need an immediate fix and which ones are acceptable exceptions. You can even use this for report validation. If you retire a column that was used in 50 different reports, finding those reports manually would take weeks of work. With Labs, you run a script that identifies every report referencing that old column. It can even auto-fix the logic if the change is simple or flag it for a human to review if it's more complex. This is the shift to governance as code. You write the scripts, version them, and run them on a schedule. Because they are automated, they aren't prone to human error or the inconsistency that comes with manual work. You move from managing one model at a time to managing an entire enterprise fleet reliably. Governance is no longer just a final checkpoint. It becomes a continuous part of how your models live and breathe. Building the data pipeline. From source to prediction. The reality of raw data is that it's messy. It lives in ERPs, transactional systems, and third-party databases designed for processing, not for analysis. To make this data useful, you first have to get it into Fabric. Everything starts in the Fabric Lakehouse. This is your bronze layer, where data lands exactly as it exists in the source system without any transformations. You aren't worried about schema consistency or quality yet because the Lakehouse acts as a staging ground for accumulating information from everywhere. Once the data is staged, your engineering team builds the pipelines that actually clean it. These pipelines handle missing values, standardize formats, and resolve duplicates to turn chaos into a cohesive structure. This creates the silver layer, which is a cleaner and deduplicated version of your records. Many organizations take it a step further by building a gold layer, which is where fact and dimension tables are finally constructed for high-level analysis. On top of this prepared data sits the semantic model. This is where the shift from engineering to meaning happens. The semantic model doesn't move data around, but it defines what that data represents by creating measures for business metrics. It establishes relationships between tables, adds hierarchies, and locks down row-level security so everyone sees only what they should. Now your predictive models can enter the picture. You open a Fabric notebook and use SemPy to pull in the measures directly from your semantic model. If you're predicting customer churn, you need historical outcomes and behavioral features like transaction size or purchase frequency. Because the semantic model already has these measures defined, SemPy retrieves them with the relationships and hierarchies intact. Your data science team then trains an algorithm on this grounded data. The model learns based on your specific business definitions, and once it's validated, it scores every active customer for churn probability. These results are written back into the Lakehouse as a new table called churn predictions, which includes customer IDs, scores, and timestamps. But the circle only closes when you connect those predictions back to the business. You create a new measure in your semantic model that reads from that churn predictions table. This measure aggregates the data by region or product so Copilot can reference it just like any other metric. When a user asks which segments are at risk, Copilot routes to this measure, applies security rules, and returns an answer grounded in your actual predictive model. This is the full pipeline. Engineering transforms the raw data, the semantic model adds meaning, and the predictive models run on that foundation. The results flow back through the semantic layer so users can interact with predictions through the same interface they use for regular analytics. The structural point here is that predictions don't exist in a vacuum. They aren't separate from your BI infrastructure, but are integrated into it using the same definitions and security. The pipeline isn't a straight line from source to notebook, but a loop that moves from the lake to the model and back to the user as an insight. This integration makes Copilot-driven predictions trustworthy. Every insight the AI surfaces has been through a structured, auditable pipeline grounded in your business rules. It isn't a black box output from a random notebook, but a properly engineered business capability. Connecting Copilot Studio to predictive agents. We've looked at the architecture in the abstract, but now we need to see how you actually wire these systems together. Copilot sits on one side and your models sit on the other, and the tool that connects them is Copilot Studio. Copilot Studio is a low-code platform for building custom AI agents that do more than just chat. It's a separate environment where you create experiences that can act, coordinate, and deliver specific outcomes. And this is where you take your predictions and make them accessible to your team in a controlled way. The process starts with a basic agent. You give it a name, define its purpose, and write instructions for how it should behave. If you're building a sales performance agent, its job is to answer questions about pipelines and forecasts while knowing exactly which data sources to trust. The real power comes when you connect this agent to Fabric data agents. A Fabric data agent is specialized because it knows how to query specific semantic models and evaluate measures. It respects row-level security and returns results with full lineage information, acting as a data-native tool for analytics. In Copilot Studio, you can connect your main agent to several of these specialized Fabric agents at once. You might have one agent for sales, one for customers, and one for the supply chain. You configure the system so that when a user asks about the pipeline, it routes to the sales agent, but when they ask about supply constraints, it coordinates between multiple agents. This is what we call multi-agent orchestration. Your Copilot Studio agent acts as the middleman that interprets what the user wants and decides which Fabric agent has the answer. The Fabric agent executes the query against the semantic model and returns the results with citations. The orchestrator then evaluates if the answer is complete before sending a natural language response back to the user. This design pattern solves the problem of scale. You can create different Fabric agents for every business domain and wire them together flexibly. It also centralizes governance because each data agent is already configured to enforce your existing security rules. You aren't managing permissions in two different places. In a real-world scenario, a user might ask why there's a variance in their region's Q3 forecast. The Copilot Studio agent identifies the intent as forecast analysis and sends the request to the correct Fabric agent. That agent queries the semantic model, applies the user's regional security rules, and calculates the variances. The user then receives a response explaining that the forecast is up 12% due to 3 large deals and an 8% increase in deal size. This insight came from a real measure in your semantic model that was secured and accurate. The system delivered a reliable answer to a specific question that wasn't even on a dashboard. This is how Copilot becomes a legitimate tool for the business. By connecting it through Fabric data agents to your semantic models, you've grounded the AI in structure. You've moved past conversational toys and built something that is secured, governed, and completely trustworthy. The role of Fabric data agents in prediction. A Fabric data agent is fundamentally different from a chatbot, and understanding this distinction is the only way to make prediction work reliably at scale. A chatbot responds to natural language by generating text, but a Fabric data agent responds to intent by executing structured operations against your data infrastructure. When you configure a Fabric data agent, you aren't building a conversational interface. You're building a query interpreter. You specify which semantic models this agent can access, and you define exactly which tables and measures it has the authority to use. You write instructions that explain how it should handle edge cases, and you might even provide example queries to guide its logic. If a user asks about revenue, you tell the agent to look for measures starting with revenue and filter by the user's region. These examples aren't conversation starters because they function as templates that guide the agent's reasoning when it encounters similar requests. This is where prediction enters the picture. A Fabric data agent understands that some of your measures are predictive by nature. You might have a measure called predicted churn risk that returns a probability, or another called forecasted revenue next quarter that returns a specific dollar amount. The agent knows these are different from standard descriptive measures. When it sees a request for a prediction, it routes to the right measure and structures the query correctly so it can interpret the results properly. This matters because predictions are incredibly easy to misinterpret. If a user asks Copilot what churn will be next month, the request is completely ambiguous. Do they want the probability for every single customer, or are they looking for the aggregate rate for the whole company? They might need it for their specific region or just one product line. A generic chatbot would simply generate a plausible sounding answer and might even invent a number to fill the gap. A Fabric data agent with the right configuration understands this ambiguity and will ask clarifying questions instead of guessing. If you've given it good instructions, it can infer context from the user's role and data access. A support manager likely wants churn predictions for their own customers, while a VP of retention probably needs company-wide totals. The agent learns these patterns and applies them. Once the agent formulates a query, it executes it through the semantic model, which is the most critical step in the process. The query goes through the exact same engine that powers your official reports. The relationships are applied, the hierarchies are resolved, and row-level security is strictly enforced. The measures are calculated using their original DAX definitions, so there is no approximation or guessing involved. There is no separate code path because the prediction moves through the same infrastructure as everything else in your system. The agent also validates the results before the user ever sees them. It checks to see if the numbers are reasonable and if they fall within expected ranges. It ensures the result has the required metadata attached, such as timestamps, model versions, and confidence intervals. This validation layer prevents nonsense results from reaching the user. If something looks wrong, the agent can escalate the issue or decline to answer rather than returning garbage data. Then we have lineage and evidence. When the Fabric data agent returns a result, it doesn't just hand over a number. It provides the full context. It shows which semantic model was queried, which measures were used, and which filters were applied. It even notes the user's role and security context at the time of the request. This lineage is the only way to build real trust. When a user sees a prediction and wants to know where it came from, the agent provides a trace that is both auditable and repeatable. If another user asks the same question, they get the same result because the same query executed through the same infrastructure. This is a massive departure from Copilot generating predictions on its own. Left to its own devices, Copilot would try to reason through the numbers and generate plausible text before moving on. A Fabric data agent executing a structured query against a semantic model returns something that can actually be tested and verified. The prediction either came from the right measure or it didn't, and the security rules either applied correctly or they didn't. These are binary facts rather than a spectrum of confidence. This is how Copilot finally becomes trustworthy. It doesn't happen by making the AI smarter, but by connecting it to systems that are structured and validated. The intelligence lives in your semantic models and your predictive engines. Copilot's only job is routing users to those systems and explaining the results. The Fabric data agent is the mechanism that makes that routing reliable. Grounding Copilot in your business context. Grounding is the word we use when everything works correctly, and Copilot's reasoning stays aligned with how your business actually operates. But grounding isn't something Copilot does on its own. It is something your architecture either enables or it prevents. Most organizations get this wrong because they assume grounding is a Copilot feature. It isn't. It is a baseline requirement. If grounding isn't there, your predictions will fail silently. Think about what grounding actually requires in a real-world scenario. Copilot needs context from 4 specific sources: the structure of your semantic model, the richness of your metadata, the configuration of your security rules, and the instructions you've provided. Each of these is a dependency. If even one of them is weak, the whole system becomes unreliable. It starts with semantic model relationships. These aren't optional extras because they are foundational to how the system thinks. When you define that a customer table relates to an order table through a customer ID, you are encoding a structural fact about your business. Copilot reads that relationship and understands that it can aggregate orders to the customer level. The join logic is implicit. Now imagine your semantic model has unclear or messy relationships. Maybe a customer ID exists in both tables, but you haven't explicitly linked them. Or perhaps you've marked a relationship as inactive because you wanted reports to use a different logic in certain cases. Copilot sees that ambiguity and is forced to guess. It might create a join that is technically valid but semantically wrong. A user asks for the average order value per customer, but Copilot routes through an unintended path and returns numbers that don't match your official reports. The user loses trust, and your team has to waste time investigating. It turns out Copilot was using an inactive relationship that nobody intended it to touch. The problem wasn't the AI's reasoning, but the ambiguity of the model itself. Metadata quality multiplies this effect. A measure without a description is a total mystery to an AI. Copilot has to guess what it means based on the name and the formula. A measure called total amount could mean gross revenue, net revenue after returns, or something else entirely. The DAX formula tells you what is being calculated, but it never tells you why. A measure with a proper description, stating it is net revenue minus approved returns in USD, removes all that doubt. Copilot reads that description and understands the scope, the calculation method, and the currency. When aggregation levels matter, the description flags it. When the measure requires specific context to be meaningful, the description explains it. Without this, Copilot makes assumptions that usually turn out to be wrong. Security misalignment creates a different kind of grounding failure. The row-level security rules you've set up for reports might not cover everything Copilot can do. A user might not be able to see a column in a report because it's hidden, but they can still ask Copilot about it if object-level security isn't configured. The data isn't supposed to be accessible, but it is. This is a grounding failure because Copilot's access isn't grounded in your actual security intent. The gap between what you meant to restrict and what is actually restricted becomes a major vulnerability. It's a subtle problem because everything seems to work without any error messages. The prediction comes back, but the user sees data they should never have accessed. Grounding requires that your security rules align with your actual intent, not just your reporting design. Instructions are the fourth and final grounding mechanism. These are the guidelines you give Copilot to help it interpret messy or ambiguous requests. If you don't provide these instructions, Copilot has to make default assumptions that might not match your business logic. With clear instructions, you can tell the AI to use net revenue when someone asks for revenue without being specific. You can tell it to only include customers who have had a transaction in the last 12 months. Now, the reasoning stays grounded in your business rules rather than the AI's own defaults. The critical insight here is that grounding isn't a property of Copilot. It is a property of the system that Copilot is querying. If your semantic model has a weak structure, grounding fails. If your metadata is sparse or your security is inconsistent, grounding fails. Copilot is just the interface, and it can only be as grounded as the infrastructure sitting underneath it. This is exactly why Prepped for AI certification is so important. It isn't about making the AI smarter. It is about ensuring the architecture beneath the AI is sound enough that the reasoning stays reliable. You are auditing the semantic model and verifying the relationships. You are confirming the metadata and testing the security. You are formalizing the instructions. All of that hard work ensures that when Copilot reasons over your data, it stays aligned with your business reality. Monitoring and auditing Copilot predictions. You have the predictive infrastructure ready. You connected Copilot through Fabric data agents, secured the perimeter with RLS and OLS, and now the users are in. They are asking Copilot for sales forecasts, customer churn risks, and revenue impacts. But this creates a new problem because now you actually need to know what is happening inside the black box. You need to see who is asking what, which predictions are driving real business decisions, and whether those predictions are even accurate. Monitoring and auditing are no longer just compliance checkboxes to satisfy a legal team. They are operational necessities for a functioning system. Every time a user asks Copilot a question, that query routes directly through your semantic model. You cannot afford for that query to be logged vaguely. You need the specifics, including the username, the exact question they typed, the specific semantic model that was hit, and which measures were used. You also need to see what filters were applied based on RLS and exactly what result the system returned to the user. This trail is your evidence that the system is working as intended, and without it, you have no way to prove why a specific prediction was made. Fabric audit logs capture this data automatically. When Copilot executes a query against a semantic model, the query engine logs the operation without you needing to add a single line of logging code. You are not instrumenting your application or writing custom scripts because the platform handles the heavy lifting for you. Your only job is to access those logs and turn that raw data into something your team can actually understand. Raw audit logs are overwhelming because you might see thousands of entries every single day. You need visibility into high-level patterns rather than individual queries, so this is where you build a dedicated monitoring dashboard. You pull the data from Fabric audit logs into a Power BI semantic model and create measures for total queries by user and average queries per day. By tracking which models and measures are accessed most frequently, you can see at a glance how the system is being used. A sudden spike in churn prediction queries might mean your retention team is responding to a market event, while a drop in forecast queries could mean users have lost confidence in the numbers. These patterns tell you if your predictive system is actually creating value or just sitting idle. Sensitivity is a major factor here because not all predictions carry the same weight. A revenue forecast that drives next year's budgeting is a high-stakes event, while a curiosity query from an analyst exploring a what-if scenario is relatively low stakes. You need to classify these predictions by risk level and then configure your governance rules to match. High-risk predictions that affect major business decisions should go through additional controls, such as requiring a manual approval or a second validation model before the data is surfaced. Microsoft Purview can help you classify these results by sensitivity, allowing you to mark high-confidence predictions as gold and experimental ones as development. Copilot respects those classifications when it decides what to show to a specific user. Data loss prevention policies also extend into this predictive space. You can set DLP rules that flag whenever someone accesses predictions about sensitive topics like compensation, health status, or creditworthiness. You aren't necessarily blocking the user, but you are creating a record and a governance event for the team to review. If someone queries churn predictions filtered by salary level, that is a red flag that needs attention. It might be a legitimate compensation analysis, or it might be an inappropriate data correlation, but the monitoring system ensures your governance team can review the intent and decide if it violates policy. This continuous monitoring approach is fundamentally different from a traditional compliance audit. An audit usually happens once a year, where an auditor reviews old data and files a report that nobody reads. Continuous monitoring happens in real time as the queries are actually occurring. You see the patterns as they emerge, which allows you to detect problems while they are still small. You can respond to misuse the moment it happens, rather than waiting for a post-mortem review months after the damage is done. The second piece of the puzzle is accuracy monitoring. Your predictive models might have looked great on test data, but you need to know how they are performing in the real world. You have to ask if the churn predictions are actually correlating with the customers who leave the company later on. To do this, you create feedback loops where you log the actual outcome once a predicted event occurs. By comparing predicted values to actual results, you can calculate model drift, which is the natural degradation in accuracy as data patterns change over time. When that drift hits a certain threshold, you trigger a retraining process so the model stays fresh and the predictions stay sharp. This is not a one-time setup that you can just forget about. It is a continuous cycle where you run accuracy checks every month and retrain your models every quarter. You are constantly monitoring real-time query patterns and updating your security rules as the business evolves. The monitoring system becomes the essential feedback mechanism that keeps your predictive capabilities trustworthy for the long haul. Governance is not something that happens after you deploy the system. It is something that runs through the entire life of the project. Common mistakes when bridging Copilot and Power BI. Let's look at what actually happens in the real world when organizations try to implement this. We aren't talking about the theory in a white paper, but the actual practice of building these systems. You build your models, you connect Copilot, and then things start to break. When they do, there is almost always a specific pattern to the failure that you could have avoided. The first big mistake is assuming that raw data is enough for an LLM to understand. A team will often point Copilot at a lakehouse full of raw tables and expect it to start making predictions immediately. They assume the AI will just know what each table represents and how they relate to each other, but it won't. Copilot sees columns with cryptic names like custody or transdt and has no idea what they actually mean in a business context. Without a defined schema or calculated measures, Copilot will generate text that sounds plausible even though the numbers are completely wrong. The user ends up blaming the AI, but the real problem is the architecture because they expected reasoning without providing any structure. The second mistake usually happens inside the data science team. A developer builds a predictive model in a notebook using raw tables from the data lake, and the model trains and generates predictions perfectly. They surface those results to the business users, but they realize too late that the model used a different definition of revenue than the official company reports. Your BI team might have a measure that excludes specific transaction types, but the data scientist didn't know that. The predictions are mathematically correct but semantically useless because they are predicting against a definition that nobody in the company actually uses. You can fix this by building the model on top of semantic model measures using Semantic Link, but teams often skip this step to move faster and pay for it later in confusion. The third mistake is treating metadata as optional documentation instead of critical infrastructure. A team might create a semantic model with clear table names, but they leave out the descriptions and synonyms. They think Copilot will just figure it out from the names, but that is a dangerous assumption. If Copilot sees a measure simply named total, It has to guess if that means total revenue, total cost, or total transaction count. That generic naming creates ambiguity that leads to hallucinations. Every table needs a business definition, and every measure needs an explanation of its scope. This isn't just bureaucracy, it is the operational infrastructure that makes your predictions reliable. The fourth mistake is what I call RLS configuration theater. A team sets up row-level security for their reports and verifies that a salesperson can only see their own region on the dashboard. They assume the security is handled, but they never actually test what happens when Copilot queries that same model directly. It often turns out that the RLS rules are too loose for an open-ended query interface. A user might ask Copilot for a comparison across regions, and while the filter applies, it might not work the way you expected in a conversational context. You have to test actual Copilot queries against your RLS rules to ensure the security model covers every possible use case. The fifth mistake is exposing sensitive columns without using object-level security. A model might contain salary information that is necessary for calculating certain high-level metrics. The team uses RLS to restrict which employees each person can see, and they think the data is safe. However, because they didn't use OLS to hide the salary column itself, a user can ask Copilot a seemingly innocent question that requires the AI to look at that hidden data. Copilot then constructs an answer that gives away compensation insights the user was never supposed to have. Hiding a field in a report UI is not real security, but OLS is, because it removes the column from the model entirely for unauthorized users. The sixth mistake is releasing these predictive models without any versioning. A model gets built and added to the semantic model, and users start relying on it for their daily work. Then the data science team retrains the model with new data, and the performance changes. Suddenly, users are getting different predictions, and they have no idea why because there is no version tracking or changelog. You should version your predictive models exactly like you would version a piece of software. Track what changed, test the new version before you release it, and make it clear to your users that the models can and will evolve over time. These mistakes are not just theoretical possibilities. They are the common pitfalls that happen when teams try to build Copilot systems without respecting the underlying architecture. If you want your system to work, you have to move past the hype and focus on the structural requirements that keep the data accurate and secure. The 2027 governance fabric, policy as code. We need to stop building for today and start looking at where this is heading, because the shift is going to be massive. Right now, governance is a manual grind involving spreadsheets, approval chains, and static configurations that usually just sit there gathering dust. By 2027, that entire model is going to disappear as governance becomes automated, embedded, and treated as a core operational power rather than a compliance headache. The reality today is that governance happens after the work is done, meaning you build a semantic model and then you have to go back to document it, set up security, and wait for certification. It is a slow sequence of checkpoints and friction that holds everything up. By 2027, this process flips on its head so that governance actually precedes creation. When you start defining a new model, the rules will apply before you even finish building it. If you create a new measure, the system will immediately check if the name follows standards, if the description is there, and if the classification is correct. If the measure fails those checks, you simply cannot move forward. Governance stops being a gate at the end of the road and becomes part of the engine itself. This is the moment where Semantic Link turns into your control plane instead of just a data access layer. It becomes the governance layer that knows your policies and enforces them every single second. You define a rule once, like requiring descriptions for all measures or classifying sensitive data, and Semantic Link acts as the enforcement engine. If a developer tries to publish a model that is missing descriptions, the system blocks it. But it won't just throw a cold error message. It will offer guidance by showing a template and giving examples of what a good description looks like. Security follows the same logic, so when you add a user to a role, your RLS rules will propagate automatically. You won't have to manually assign that person to every single model because the system will recognize the group change and understand exactly what they should see. It looks at the policies and classifications, then applies the correct RLS rules across every relevant model in a matter of seconds. A person goes from having zero access to being fully configured without any manual intervention or forgotten models. Consistency is finally enforced by design. When you decide to expose a semantic model to Copilot, the security checks will run on their own to ensure everything is ready. The system asks if the model is prepped for AI, if the RLS and OLS are tight, and if the instructions match the data classification. These are not optional steps that a busy developer might skip over. They are mandatory gates that prevent a model from reaching Copilot until it passes every test. The pieces of this technology are already here, and tools like Semantic Link Labs are already automating governance at scale for early adopters. By 2027, this will be the mainstream way of working and will be just as central to Fabric as the data warehouse itself. You won't even think of it as a separate task, because it will just be how the platform functions. This shift changes everything for your governance team because they can finally stop doing manual reviews and start writing code. They design the rules once, publish them, and the system handles the enforcement everywhere and all the time. Their effort moves from being a bottleneck in the approval process to being the architects of the system. Instead of looking at models one by one, they are building logic that governs hundreds of models simultaneously. It also makes governance visible and measurable in a way that actually makes sense. Most compliance reports today are backward-looking documents that show you what happened last month. But by 2027, your dashboards will show compliance in real time. You will know instantly if every model meets the standard and if every user has the right access. If an RLS rule drifts or changes, the system detects it immediately. If that change violates a policy, you get an alert, and if it was intentional, you document it right then and there. The mindset shift here is just as big as the technical one. Today, builders see governance as something forced on them, but in the near future, it will be a tool they actually use to move faster. It removes the guessing game about what is required and makes it nearly impossible to accidentally break the rules. The governance fabric is not a wall designed to slow you down. It is a set of guardrails that lets you run at full speed while staying completely safe. This is the path we are on, so you should start thinking about it right now. When you build models today, design them to be ready for this automated future by using clear names and writing solid descriptions. The organizations that get this right early will be able to scale their AI capabilities much faster than the ones still stuck doing manual paperwork in 2027. Starting your implementation, first steps. You have seen the full architecture now, from semantic models as meaning layers to semantic link acting as the bridge for prediction. We have covered how data agents talk to Copilot and why monitoring is an operational must-have. Now we have to get practical and figure out where you actually start building this in your own organization. The first step is an inventory audit to see exactly what you are working with. Open up your Fabric workspace or your Power BI premium capacity and make a list of every single semantic model you own. For every model on that list, you need to check the metadata to see if the tables have business descriptions and if the measures are clearly defined. Most companies find that about 40% of their models are in good shape, while the other 60% are missing basic info. That is not a failure on your part, but it is a baseline that tells you exactly where you are starting from. Use a simple color code where green is complete, yellow is partial, and red is missing. Once you see the patterns, you will know which teams are doing well and which legacy models need the most work. While you are digging through the metadata, you need to go talk to your users to find out what they are actually asking Copilot. Don't guess what they want, but instead have real conversations with your power users to see where they are struggling. Ask them what questions they wish they could ask but can't get an answer to right now. You will start to hear the same things over and over. Sales teams usually want better forecasts, finance wants to understand variances, and operations is looking for anomaly detection. Your job is to find the overlap between what the business needs and what your data can actually support. Once the audit is done and you have your use cases, pick one single target to start with. Do not try to fix the entire company at once, but instead choose one prediction domain like sales forecasting or customer churn. Pick something that solves a real problem but is small enough for your team to build in a reasonable amount of time. It is much better to build on an existing semantic model than to try and start from absolute zero for your first project. Now it is time to build that first predictive model. Open a Fabric notebook and use SemPy to pull the measures directly from your semantic model so you aren't redefining things like revenue. You use those existing measures as your foundation and then build out your features like customer segments or transaction history. You gather your training data, run the model, and validate the results. Once you are sure the numbers are right, you run the prediction for your entire population, whether that is every customer or every open sales lead. You need to store those predictions back in the lakehouse in a table with a very clear name like churn predictions. Make sure you include the primary key, the prediction itself, and a confidence score so people know how much to trust the data. This table becomes the official source for your new predictive measures. Now you can wire that data back into your semantic model, create a new measure that reads from the prediction table like average churn risk, and suddenly it is available for everyone to use. Copilot can see it, and your data agents can query it because it is now a native part of your semantic layer. Before you turn it on for everyone, mark the model as prepped for AI and go through your certification checklist. Double-check that the naming is crystal clear and that your security settings are locked down tight. Write the AI instructions that tell Copilot how to interpret these new numbers and run some test queries to make sure the answers make sense. This is how you build trust in the system before the rest of the company sees it. The final step is to create a Copilot Studio agent that connects to this model as a data agent. Keep the scope very narrow at first by focusing on that one specific use case and testing it with a small group of people. Watch the questions they ask and see where the system gets confused. Every time a user asks a question that fails, it tells you exactly how to improve your semantic model. This is your first cycle, and it is small on purpose. You are learning the ropes and proving that the architecture actually works in the real world. Once you have one successful loop finished, you can start to scale up by adding more models and more domains. But before you try to go big, you have to prove the pattern works right here. Building a sustainable predictive AI practice. You've built your first predictive system and it actually works. Users are asking Copilot questions and predictions are flowing through your semantic layer without a hitch. But now you face the real test that determines if this is a permanent capability or just a one-off project. You have to make it operational. That requires structure, clear ownership, and a real commitment to the process. It starts with ownership. Every single piece of your predictive infrastructure needs a dedicated steward to look after it. Think about who owns each semantic model. I don't mean the person who created it once and walked away. I mean the person responsible for its accuracy and fitness for use every single day. This person is the one who gets the alert when metadata is outdated or data quality starts to drop. They approve model retraining and they are the first line of defense when users run into trouble. You need to assign this role explicitly and make it a formal part of a job description rather than just an assumption. The predictive models themselves need a different kind of owner. These are the machine learning models running in your notebooks, and they require constant attention to stay relevant. They need versioning, regular retraining as data patterns shift, and active monitoring to catch accuracy drift before it causes problems. Usually your data science team or whoever maintains your analytics infrastructure should take this on. They aren't just responsible for the initial training, but for the long-term performance of the model in the wild. Then you have governance and compliance. This is where your policies live. You need a person or a team to define the standards for naming, documentation, and security configurations. They conduct the audits to make sure everyone is following the rules, but they also approve exceptions when a policy needs to bend for a legitimate reason. This team maintains the playbooks and updates them as your requirements evolve over time. In most organizations, this ends up being a specialized subset of your BI or governance group. Next, you need to look at your processes. You have to establish exactly how a new predictive model moves from a development environment into full production. This isn't about creating a committee to slow things down with red tape. It's about quality gates. A data scientist develops a model in a dev workspace and validates it against test data. They document what it predicts and how it works. Then they submit it for a structured review. A peer from the BI team checks the semantic model grounding, while the governance team reviews it for compliance. Once they both sign off, the model moves to production and becomes a new measure that Copilot can query. Don't forget about a retirement process because predictive models do not last forever. Business conditions change and data patterns shift, which means a model trained on 5 years of data eventually becomes stale and misleading. You need an explicit way to retire old models, perhaps through an annual review where every model is evaluated for its continued relevance. If a model isn't being used or the accuracy has dropped below an acceptable level, you mark it as deprecated. You stop exposing it to Copilot and you tell your users so they can find a better alternative. Active management means you don't just let things decay in the background. Training is another critical piece of the puzzle. Your teams need to deeply understand Semantic Link and they need to know exactly what SemPy can and cannot do. They have to grasp why grounding matters so much for reliability. Governance shouldn't be seen as a boring compliance burden, but as the very infrastructure that makes your predictions trustworthy. You can achieve this by running workshops, creating internal documentation, and building templates. Your goal is to make it easy for a new hire to step in and understand exactly how predictive systems work in your company. You also need to track the metrics that actually matter. To understand if this practice is delivering real value, you should track how many users are actually asking Copilot for predictions. You need to measure accuracy by seeing if those predictions correlate with real-world outcomes. Most importantly, look at the business impact. Are these predictions changing decisions for the better, and how fast can a user go from a question to a solid prediction? These numbers will tell you if you're building something meaningful or just maintaining a system that nobody uses. Finally, you need an iteration rhythm. Set up quarterly reviews to look at what worked and where the predictions failed. Listen to user feedback and adjust your processes accordingly. You might find that your governance is too restrictive, or perhaps it isn't strict enough to keep the data clean. Maybe the teams need more hands-on training or the documentation is too confusing. Every cycle is an opportunity to learn something new and evolve the practice based on reality. This operating model is the line between saying we built a Copilot system and actually running a predictive AI practice. One of those is just a project, but the other is a core capability. The difference always comes down to structure, ownership, and a commitment to continuous improvement. The gap between Copilot and predictive analytics isn't a limitation of the technology, but a problem with the architecture. Copilot doesn't do the heavy lifting of calculation because its job is to orchestrate. Your semantic models grounded in Semantic Link are what actually do the math. Your data science teams are the ones building the engines in their notebooks, and your governance framework keeps the whole system trustworthy. It all starts with metadata. From there, you move to SemPy and connect everything through Fabric data agents. Once the technical pieces are in place, you build the operating model that keeps it all running. By the time we reach 2027, this approach will be the standard way of doing business, so the best time to start is right now. If you want to stay ahead on Microsoft 365 Copilot and the modern workplace, make sure to subscribe to the channel. If this was helpful, leave a review and let's connect over on LinkedIn.